Next, we're going to look at a couple of element effects. And as we look at these effects, what we're going to have is a proton bonded to some atom in a molecule. And what we're going to be doing is analyzing the identity of this atom that the proton is bonded to. So what we're going to do is, when we do a comparison here, we're going to look at changes in this atom and how that affects acidity. There's two element effects we're going to talk about: electronegativity and atom size. So let's start with electronegativity. And when we're using the electronegativity effect, we're comparing atoms in the same row. And what we find is that the hydrogen bonded to the more electronegative atom is more acidic. Okay, but I'm even going to highlight this to drive home the point. We're comparing atoms in the same row for electronegativity, not up and down on the periodic table. Even though there is electronegativity trends there, in that case, we'll be looking at something different. So now if we look at just a cross section of the periodic table here, we're just considering going across a row. We have increasing electronegativity going from left to right. So in just a simple sense, if we compare the hydrogens on carbon over to fluorine and compare CH4, NH3, OH2, and FH, as you go from left to right, we're increasing acidity. In fact, the jumps are quite big. If we look at pKa values, the pK of CH4 is about 55, NH3 about 35, water is about 16, and HF is about 3. So large jumps going from left to right. Now, why is this? Well, remember, we can figure this out by analyzing conjugate base stability. And if you compare, let's do the two extremes. The conjugate base of CH4 would mean a base takes away one of the protons and leaves you with CH3 minus. The conjugate base of HF is F minus. Well, which negative charge is going to be more stable? The one on the more electronegative atom. So because that's a more stable conjugate base, then the corresponding acid is a stronger acid. It's more willing to donate its proton because what you get is more stable. CH4 is not willing to donate its proton because what you get is not very stable at all, a negative charge on a carbon. If we want to compare maybe a slightly larger molecule, let's say you're asked to figure out which one's more acidic between, this is called propanol versus propylamine. So in both cases, it's the hydrogen on the electronegative heteroatom that's going to be the most acidic. But now, draw the conjugate base for each. Here's O minus and H minus. Which negative charge is more stable? The negative on the nitrogen or the negative on the more electronegative oxygen? That's the more stable conjugate base. Because the conjugate base is more stable, the acid that it came from is the stronger acid. The second effect we're going to look at is atom size. Again, this is an element effect because we're analyzing the atom the hydrogen's bonded to, but we're going to look at how changes in the size of the atom affects the acidity. Now we're going to be comparing atoms in the same column. And what we're going to find here is that the hydrogen bonded to the larger atom is more acidic. So again, let's look at a cutout from the periodic table. And with this, what we know is that as you go down the periodic table, you're increasing atom size. Let's start with the halogens, because most people will often incorrectly think HF is the strongest acid and HI is the weakest acid because of electronegativity. But it's actually the total opposite. So in terms of acidity, HF is the weakest acid, HCl is a bit stronger, HBr is a bit stronger than that, and HI is even stronger than that. So why is that? Well, once again, let's compare the conjugate bases. The conjugate base of HF is F minus. The conjugate base of HI is I minus. In terms of the atom size, fluorine or fluoride is very small and compact. Iodide, however, is much larger. What that larger size does is it spreads out the negative charge better. So what that means is I minus is the more stable conjugate base. F minus is the less stable conjugate base. Since I minus is the more stable conjugate base, HI is the stronger acid. Let's do one more comparison. Say you want to compare OH versus SH versus SEH. So with these, as you go from oxygen to sulfur to selenium, the size of that atom becomes larger. And for the same reason we discussed above, the larger selenium is going to be the most acidic. The smaller oxygen will be the least acidic. Again, this type of comparison, we're comparing atoms in the same column. And even though we do have electronegativity trends here, don't worry about electronegativity. We're looking at size. So despite F being more electronegative than I, size wins. Despite oxygen being more electronegative than selenium, size again wins. Even if you happen to have charges in your molecule, they're going to follow the same trend. So just looking at an example here, if we go from an uncharged acid like NH3 to a corresponding charged acid, NH4+, that's going to be more acidic. But then if you compare similar charged compounds, you follow the same trends that we discussed. So going from NH4+ to H3O+, you're going from nitrogen to oxygen. That's the electronegativity trend. And H3O+ is more acidic than NH4+. Next, if you go from H3O+ to H3S+, or H3S+ to H3 selenium plus, you're also going to be increasing acidity because now you're going down the periodic table.